Welcome back. We will continue our discussion on design of atomizers. We will start by looking at the simplest of all, which is the pressure swirl atomizer, and try to understand a formal design process that we can use to design a simplex atomizer. Now, before we go much further, it is always a good exercise to first have a schematic of what you want your atomizer to look like and the various degrees of freedom that you have available to you at your disposal, say whether it is an orifice size or any other dimensions in there, these are all degrees of freedom that you have available at your disposal, and you have been given a certain set of constraints that you have to meet. So, like for example, you may have a certain supply pressure that is available to you, and you want your atomizer to spray a certain fluid at a certain flow rate. These are all design constraints that you have to obey at the end of your design process. Okay. So, we will start our discussion of design of simplex atomizers. Okay, this is going to closely follow a paper by Chu et al. I will give you the reference, it is AIAA journal volume 42 12 from December 2004. In fact, their process also follows the original work in this field by these two people. This is a classic paper where the first design process for a simplex atomizer was presented. Now, we looked at let us first draw a schematic of this whole of what it is that we are talking about. Okay, we will start by looking at the schematic itself. The atomizer that in question has two parts to it usually. There is a fuel distributor. So, this we will call this part distributor, and this part is often called the orifice plate. So, the simplex atomizer at its heart has two parts to it. Now, the distributor element has a set of tangential slots, and in this case we have shown those to be at some angle beta, and so they are bringing in fluid into this passage here. I will I'll sketch this just to show you. This is all like the passage that is enclosed by the distributor and the orifice plate. I am going to erase this. I just wanted to show you the basic idea of how this works. So, all of the part that I hatched in yellow could be wetted by the liquid that you are trying to spray. So, that is the geometry we are looking at. Now, the distributor element brings in fluid at some angle beta, as well as it having a swirl component. So, if I look at the top view of the distributor plate, essentially it could be a set of slots. Let us say I am showing in this case 2 slots that are coming in at some off axis location R I. The off axis location R I dictates the amount of swirl. Now, I have shown the swirl chamber here to be slightly larger than R I itself. So, the distributor slots are not exactly at the very tangential edge of the swirl chamber, which is sort of more like a practical situation. Now, in this case essentially what we form, because the liquid coming in is at a tangential, has a tangential velocity, you create a swirl in this plane, and that swirl sets up a free vortex inside this region. For a free vortex, we saw that the total angular momentum is conserved, because there is no dissipation, because the flow is irrotational. For a free vortex, the angular momentum is conserved, which I can write as follows. If I want to know what the swirl velocity is at any r location, and if W I is the swirl component of the velocity at the inlet, R I is of course the radius of the slots in the distributor. Now, I could have, like I have shown in this picture, 2 slots, but I could have multiple slots. So, at any r location I have W I. Now, just to clear what W I is, W I would be q times sin beta divided by A P. A P is the total area of all the slots put together. So, for example, in this case, if W is the width and if d is the depth, n times d times w is AP. Okay. Before we go much further, let us write down the list of givens. So, what are all the degrees of freedom that are available to us in the design process and typical constraints. For example, the degrees of freedom available to me are n, d, w, r I, r s, I will add a few more if this is L s and if this is L o. So, L s is the length of the swirl chamber, L o is the length of the orifice, exit orifice, and of course, r o that I have shown here, which is the radius of the exit orifice. Now, I could also have, let us say, this angle here alpha, the angle of convergence. These are all parameters that are important. Typical constraints that we have to meet are supply pressure is usually specified, flow rate that you want the nozzle to deliver is usually also specified. So, that is Q, we will say that is in meter cube per second, this is in pascals or bar typically. Let us be more engineering rather than SI units, we will say this is specified in bar, this may be specified in liters per hour or liters per second. I have a certain cone angle that I require, say for example, in this schematic it could be that angle there of the liquid sheet exiting the nozzle. And in more recent instances, you may have some sort of an indication of some sort of a requirement coming from drop size. I will use a script D for this. Although we will very quickly see that it is going to only be known after the fact, not really controlled during the design process. Okay, so if I now go back to my free vortex that I have set up by these tangential slots, W times R is W I R I, which is coming from angular momentum conservation. Now, mind you, the moment I say angular momentum conservation, I have already made a couple of simplifying assumptions that we are only dealing with inviscid analysis. Actually, angular momentum conservation alone does not require inviscid it could be true even in a viscous flow, but we are only going to look at an inviscid analysis, as you will see a little later on. Now, since we made the simplifying assumption of the flow being inviscid, I can now use Bernoulli's equation at any, if delta P is the supply pressure, P is the static pressure at any point in the chamber, U is the axial velocity, W is the swirl velocity. Now, if I go back to the schematic, we talked about this in some detail. One of the main advantages of using a pressure swirl atomizer is the fact that it entrains an air core. So, your orifice size is no longer the determinant as far as the length scale of the liquid coming out of the nozzle. The length scale associated with the liquid can be much smaller than the orifice size itself, and that is one of the advantages of having the pressure swirl like design. Okay. So, let us see what that means here. What that means, what I have shown here in blue is the air core itself. And I am going to call the air core radius as ROA. We will see that it does have a significant bearing to the performance of this nozzle. So, if I have ROA as being the radius of the air core, I can apply the Bernoulli's equation from between the 2 points. If I take a point way upstream here where the pressure is delta P, and if I apply it to a point on the air core here. So, I am applying Bernoulli's equation between this point way upstream of the atomizer where the fluid kinetic energy is very small and all of the, and basically U and W are 0, and to a point just on the liquid, in the liquid, but on the air core periphery. So, if I apply Bernoulli's equation between these 2 points, what do I get? I find that delta P is equal to half rho U 0 A squared plus half rho W O A squared, where U 0 A is the axial velocity at the air core and W 0 A is the swirl velocity at the air core. I think at this point it is good to take a small detour down the lane of undergraduate fluid mechanics again. Remember, Bernoulli's equation is only applicable on a streamline. Now, if I take a streamline coming to this air core all the way extended into the tank. So, if I can draw a streamline going from this point here all the way into the tank, which is at some high elevated pressure delta P, we are applying this Bernoulli's equation on that streamline. I can also apply it from that same tank to another point, let us say here or here, does not matter, but if all the streamlines are originating from the same tank, I can apply this Bernoulli's equation between any point inside this swirl chamber and the tank, okay, which also means since the tank is at a constant supply pressure delta P, it also means I can essentially apply Bernoulli's equation between any 2 points inside the swirl chamber even if they are not on the same streamline, because I can apply Bernoulli's equation on two points on a given streamline, and if all the streamlines are originating from the same stagnation pressure delta P, I can essentially apply Bernoulli's equation even across two streamlines at two different points, because they are all amounting to the same stagnation pressure. We will take advantage of this later on. So, now back to, so we have our delta P, which is half rho u 0 a squared plus half rho w 0 a squared. Now, what is u 0 a? That is the axial velocity in this region. And w 0 a happens to be the swirl velocity. So, we will write some simplifying expressions for that. U 0 a would then have to be q divided by a 0 minus a 0 a. Okay, a 0 a is the area of cross section of the air core. A 0 is of course pi r 0 squared. W 0 a I can get from our angular momentum conservation as that q r I over A p is the linear velocity or speed of the liquid coming in. So, let us make some notes here. This velocity vector has a magnitude of q over A p, and the component that is in this plane here is q A p sin beta, and that times r I is the angular momentum essentially, times rho of course, but we are going to instead of writing rho V r, we are just going to write V r because rho is constant everywhere. Okay, so, I can now substitute these two equations into the Bernoulli's equation at the air core. What do I have? Delta P would then become half rho Now, we define a discharge coefficient just like we would define, let us say, for flow in a pipe or flow past a flow through an exit orifice or sorts. We were actually introduced to this earlier on. We used the terminology flow number, and we showed how that flow number is going to be dependent on some system of units that you have. We are now going to define figure out a way by which we can make it relatively unit independent. Okay. So, I can now define a discharge coefficient as follows. Q by A naught is the, So, A naught is like the total cross sectional area available for the flow. So, we are defining this discharge coefficient as though we have no swirl, it is just flow through an orifice. When I substitute q from this expression into the equation for delta p, after some just a couple of simplifying steps, we find this. I have introduced a couple of new terms, new symbols here. Let me go ahead define them. X is A0 A divided by A0, which is like the fraction of the cross sectional area that is occupied by the air core. X is physically the fraction of the cross sectional area that is occupied by the air core. K1 is this dimensionless group AP over pi R0 RS. Okay, you can clearly see K1 is dimensionless, so is X. So, I now have an equation relating CD to X and I also have K1. Now, K1 is what I am after, K1 is something I need to get a value for before I can design. CD is something that I may actually know apart from A0. So, if I assume an A0, if you look at this expression here one more time, if I know A0, I know CD because Q and delta P are given to me in the form of constraints. I have a supply pressure and I have a flow rate I need to deliver. So, for a given A0 I can find a CD. So, if I have a CD, I still have only one expression down here coming from our Bernoulli's equation, which relates K1 and X. X is still something we have no handle over, that is determined by the fluid mechanics inside the atomizer. Okay. Apart from of course Ri over Rs and sin beta, these are all also design variables, degrees of freedoms that are available to us, and we have only one expression. So, herein comes a simple principle that is often invoked to fix the value of X. Okay, this is called the principle of maximum flow which says that X X will adjust to give the maximum flow for a given supply pressure. Okay, what does this actually, how does this work physically? Just to sort of pose some arguments. If I have an orifice and let us say X is the cross sectional area that is obscured by the air core. If X were large, then you can sort of imagine that the back pressure behind inside the swirl chamber would be larger. So, essentially that force would cause more liquid to flow, causing the air core to shrink. If the air core was too small, then the pressure there would be low, that the pressure outside, the ambient pressure, would push the air core out to a larger diameter. So, these two forces would balance themselves, where the air core has such a diameter that the flow through is at a maximum. Okay. This is not really something that can be proved other than through like posing simple arguments, but it is often invoked in fluid mechanics systems to give us one more equation, so to say. Okay. So, let us see what that does. So, we have an expression here relating 1 over C d squared to x, and one way of employing this is to set d dx of 1 over C d squared equal to 0. So, essentially d C d dx is equal to 0 is the same as writing this expression, and when I do that, what do I have? I will find k 1 squared So, I have a value for k 1 related to x now. This is coming from this principle of maximum flow. If I substitute this back into my expression for C d, we end up getting this equation C d So, if I give you a C d, here is a nice expression that gives you the value of x, value of the air core diameter. Okay. Essentially, if I know C d, I can solve this into a cubic equation, cubic polynomial equation for x, that usually has 2 complex roots and only 1 real root. So, you are guaranteed to get a value for x that is real, and usually between 0 and 1, that is what you want. And now, if I from this definition of x, I can define a non-dimensional film thickness if I define a T star to be R 0 minus R 0 A divided by R 0, you can quickly see how that definition is the same as 1 minus square root of x. X is A 0 A divided by A 0. So, square root of x is the same as R 0 A divided by R 0. So, what have we done here? Essentially, if you tell me, let us go back to the list of constraints that we have, these are what we want to meet. So, if you give me a delta p and a q, I am going to assume an R 0, I am only going to assume an exit orifice diameter, and for that exit orifice diameter q and delta p, I can find C d from this expression. That is the basic definition of what a discharge coefficient is. Once I know a value for C d, I can come back here and get a value for x. Once I know a value of x, I know the non-dimensional film thickness coming out of the nozzle. Now, why is the non-dimensional film thickness important? Because that has a bearing on the drop size. Okay. So, if I know delta p, q and a 0, I have a way of estimating what the drop size would be. So, if I know T star and if I know the fluid mechanic properties of the film coming out, let us say the swirl velocity, the axial velocity, the air density, I can use linear instability calculations to find the maximum, the most unstable wavelength on that film, and from the most unstable wavelength I can estimate a drop size. So, it gives me an estimate for what the mean drop size would be coming out of the nozzle. There is also another side to this, which is coming back from the cone angle. A simple trigonometric calculation would tell us that the cone angle is that so where W 0 bar is the mean swirl velocity at the exit, and U 0 bar is the mean axial velocity at the exit. We can also rewrite this where u is the speed at exit given by root of W 0 bar squared plus U 0 bar squared. Okay, and I can write a simple expression as u times a 0. This is the basic definition of any discharge coefficient. U times a 0 is the theoretical flow rate, q the actual flow rate divided by u times a 0 the theoretical flow rate is the discharge coefficient. Now, I need an estimate for W 0 bar before I can tell you what sin theta is going to be. So, for that we are going to use the idea that we have a free vortex inside the swirl chamber. So, free vortex has a 1 over r dependence of the swirl velocity with the radial coordinate. So, we will take advantage of that, and once I do that, the total angular momentum at the exit is given by integral going from r 0 a to r 0 of 2 pi r. This is actually better stated as angular momentum flux at the exit. So, it is like how much angular momentum is exiting the swirl chamber at this point. So, the exit is essentially the mass flow rate times the angular velocity associated with the mass flow rate. So, I have 2 pi r rho u 0 bar dr. U 0 bar is the mean axial velocity. That axial velocity is actually what is carrying the mass out of the nozzle. The swirl velocity is not carrying mass out of the nozzle, because V dot dA, which we are used to in control volume analysis, for the swirl would be 0. Okay, so the mass is being brought out of the nozzle by the axial velocity, and this rho u0 bar is the mass flow rate, is rho u0 bar times 2 pi r dr is like a differential cross sectional area at a radius r. This is the actual differential mass flow rate coming out of a thin slice dr width at some radial location r. This times q r I divided by A p r sin beta. So, q r I sin beta divided by A p is the swirl velocity at the inlet, is the angular momentum at the inlet, that divided by r. Remember, our very first expression said at any point I have this W at any point inside the flow, inside the swirl chamber, times the radial location of that point is equal to W I R I, and W I is given by q sin beta divided by A p. A p is the total area of all the slots, as a reminder. So, this, if I do the integration, I can cancel out r here, and essentially what do I have? This gives me you essentially have a constant, the only and integral dr going r0 a to r0 gives me just the difference between the radii. The total mass flow rate exiting the nozzle is rho u0 bar times a0 minus a0 a. This is just the cross sectional area available to the fluid flow A0 minus A0A times U0. It is like the basic definition of mean axial velocity. So, therefore, if this is the total angular momentum that is being carried out by this mass flow rate, the angular momentum divided by the mass flow rate is like the mean swirl velocity. The angular momentum flux, see the word, I am not being very careful here, flux is actually a word used to indicate per unit area. Okay. So, this is actually the total angular momentum flow, it is actually total angular momentum rate, and so if I take the mass flow rate in the denominator and take the angular momentum rate exiting the nozzle, and take the mass flow rate exiting the nozzle, this ratio is essentially what the average swirl velocity would be. So, if I do that, what do I have? This is a simple division of these two quantities we identified. W0 would then become 2 pi q r I r 0 minus r 0 a So, if I invoke the definition of sin theta that we put up there, we will find that is equal to pi over 2 C d sin beta times R I over R s. In here I have added another k here, which is essentially A p divided by d s d 0. It is simply pi over 4 times the k 1 that we had defined earlier. We had defined a k 1 as A p divided by pi r s r 0, k is just pi over 4 k 1. Okay, so let us quickly recap and write down the design procedure. Okay. So, first calculate C d. So, the first step starts by assuming R 0. And then you calculate C d, and from the calculated C d you get calculate x, and then from there you can calculate k and k 1. K is a dimensionless group that involves some of your degrees of freedom, areas of the ports, d ds, d 0, etc. Okay. So, I now have a way of going from a flow rate to, by assuming R 0, which is one of my degrees of freedom, I can get some constraints on the other degrees of freedom. So, design is always an open ended problem, that there are multiple solutions to a given set of constraints. If you go back to the list, we clearly had more in our degrees of freedom list than we had in our constraints, and that is always going to be the case irrespective of where you go. Okay, that is the way good design process always works. So, we are still left with some degrees of freedom that we have to use to our advantage to achieve other constraints that are not explicitly laid out in quantitative terms. Like for example, you may have constraints coming from uniformity of the spray, you could quantify it. You could have constraints coming from manufacturability, tolerancing. You could have constraints come from other performance issues such as drop size, we have not talked about that. So, there we will look at a couple of examples in the next class where we will attempt to apply this design procedure and reach a set of values for our design, for our degrees of freedom.